Hello students, myself Dr. Pramod Kumar Shivajirai Hire. I am professor and head of the Department of Geography, HPT Arts and Arvake Science College Nasik. Today I am going to talk to you regarding Pearson's product movement correlation coefficient. We will today see how to calculate the Pearson's product movement correlation coefficient. But the Pearson's product correlation coefficient, which is denoted by small r, is suggested by Carl Pearson. It is one of the most powerful and widely used technique of correlation. It measures the relationship between two variables and it is represented by small r. The values of r varies from -1 to +1 and it is a unitless quantity. The r is calculated by following formula. This is the formula of the correlation coefficient. R is equal to summation of x into y divided by n minus x bar into y bar divided by standard deviation of x and standard deviation of y, where r is correlation coefficient, summation xy is summation of product of x and y, n is the number of observations, x bar is mean of x, y bar is mean of y, sigma x is standard deviation of x, sigma y is standard deviation of y. Since the numerator is also called as covariance of xy, the formula can also be written as under r is equal to covariance of xy divided by standard deviation of x into standard deviation of y. Therefore, it is first necessary to calculate the standard deviations of x and y, and that we can calculate with the help of following formulae. Standard deviation of x is equal to under root of summation of x square divided by n minus x bar bracket square. Standard deviation of y is calculated in the similar manner, which is equal to under root of summation of y square divided by n minus y bar bracket square. Let's see the example for calculating Pearson's product movement correlation coefficient. The example is calculate Pearson's product movement correlation coefficient, that is small r, for the given data. The figures are measurement of two variables that are soil moisture content and the number of trees. Find out the explained variance. Test the correlation at 0.05 and 0.01 level of significance and interpret the results. So let's see in what way the calculations are carried out. This is the table of the data set for the number of trees, which is x variable, and soil moisture content, which is y variable. So initially the data have been given in two columns. In the examination, the data may be given in the form of the rows, which you'll have to convert in columns. Then we have to find out some calculations. We have to calculate x square, we have to calculate y square, and the product of x and y. Say for example, the square of 47 is 2290, the square of 21 is 441, and the product of x and y is 987. So in this way, we can calculate x square, y square, and the product of x into y. Whereas in the first column at the end, we have to sum up all the variables of all the atoms of x, whose summation is 500, and there are total 10 numbers, so the n is 10. In the similar manner, we have to add up all the atoms of y. Its summation is 300 and the total number of observations are 10. The summation of x square is 27,818, whereas the summation of y square is 10,462, and the product of x into y are calculated in this column, and the summation of x into y is 16,837. So in this manner, we have to calculate x squares, y squares, and x into y, their summations, and the total number of observations. Now this is the way for calculating standard deviation of x and standard deviation of y. As the formula stated in the beginning, standard deviation of x is equal to under root of summation of x square upon n minus x bar square. So summation of x square is 27,818, and the number of observations are 10, minus x bar is 50, the square of that comes 2,500. So this division has been carried out, and this is subtracted, 2,500 is subtracted, and the answer that comes 281.8. And if we remove the square root, the standard deviation of x is obtained, that is 16.79. In the similar manner, standard deviation of y is calculated, that is under root of summation of y square upon n minus y bar square. Summation of y square is 10,462 divided by number of observations 10, minus y bar is 30, so the square of 30. Square of 30 is 900. This division is made, that is 146.2 minus 900, that comes the answer. And the standard deviation of y is 12.09. So we have to put the values in the formula of correlation coefficient, that is summation of xy minus x bar into y bar divided by standard deviation of x into standard deviation of y. Summation of xy is 16,837 divided by 10. The total number of observations, whether there are 10 pairs, one is for x and other is for y, minus x bar is 50 into 30 divided by standard deviation of x is 16.79 and that of y is 12.09. So this division and this subtraction is carried out, this multiplication is carried out, so the subtraction is 183.7 and multiplication results into 202.99, and in this manner we can calculate the Pearson's product movement correlation coefficient, which is 0.905. We have to remember that the product movement correlation coefficient vary between -1 and +1, and a calculated value falls between -1 and +1, with 0 indicating no correlation. The value of R is 0.905, which is positive, indicating very strong positive correlation between soil moisture content and number of trees, as these were the two variables we have taken for calculations. We also are required to calculate the expand variance, which is simply the R square. Therefore, the R square is 0.819. We can get it in percentage multiplying by 100, that comes to 81.90%. That is 81.90%, or about 82% if we round up. The relation between the soil moisture content and number of trees is so strong, that is about 82%. We are also required to calculate the significant testing in correlation analysis. In order to test the level of significance, following formula is used. That is, T is equal to R into under root of n minus 2 divided by 1 minus R square, where T is the test of significance, or the level of significance that shows. N minus 2 is degrees of freedom, and in this case the degrees of freedom is 10, because we have 10 observations, 10 for x and 10 for y, but we have 10 pairs. That's why the degrees of freedom is 10 minus 2. So that comes to 8. The degrees of freedom is 8. To test the level of significance, we have to refer the distribution of T at n is equal to 8, at 0.05 and 0.01 from the statistical table, from the standard statistical table. So T is calculated in this manner. The formula was already explained to you in the earlier slide. So R is 0.905 into under root of, there are 10 pairs minus 2, 1 minus explained variance R square is 0.819. We have to do this subtraction, that comes 8 divided by 0.181, and this division is done, and the answer is 44.19. If we remove this under root, that comes to 6.647, and this is multiplied with R, and we get the value of T, that is 6.01. It is the calculated value of the T. But this calculated value, we have to compare the value that we get in the statistical table, that is the distribution of T. As you know, our degrees of freedom is 8. So we have to see in this column of degrees of freedom at the level 8. We have to first calculate for 0.05. So the value for 0.05 is 1.860, and the value for 0.01 is 2.896. So at 0.05 level of significance, our tabulated value is 1.860, and for 0.01 level of significance, that is 2.896. So we have obtained these values here for 0.05, as I have said, 1.860, and for 0.01 level it is 2.896. When the calculated value, that is our calculated value of t, is more than the tabulated value, means these values, then we can say that the correlation is statistically significant, and that is only the testing of level of significance. So since our calculated value is 6.01, the calculated value of t is 6.01, which is greater than the tabulated value of t, that is 1.860 for 0.05 and 2.869 for 0.01 level of significance respectively. Therefore, we can say that the correlation is statistically significant at both the levels, means at the level of 0.05 and at the level of 0.01. That is, in other words, we can say with 95 as well as with 99% of confidence, we can say that there is strong relationship between soil moisture content and number of trees. This is the declaration of my presentation, and I thank you all for paying attention. Thank you very much.